Welcome to my talk. So our group has been working on quantum computing from many different aspects, especially about the domain-specific language design, compiler optimization, and computer architecture design and automation. Today, I'm going to share my recent work about how to do quantum program testing on a real quantum computer. And in this talk, we will start from the motivation about why do we need quantum program testing and debugging, and then what is the key challenges here compared to the classical debugging and testing. And then we want to introduce our solutions, the projection-based assertion, its theoretical foundation, and also some practical issues when implementing this kind of assertions on real quantum devices. At last, I will conclude the talk with some key takeaways and some interesting extended usage of such projection-based assertions beyond testing and debugging. For example, we can also use this kind of assertion for program optimization and error mitigation. And note that many of the technical details can be found in our OOPSLA paper, and we refer interested audience to our paper for further readings. And first, why do we care about quantum computing? As you may know, quantum computing is already the new race to the moon with national pride. Besides the efforts from academia and the dedicated faculty high, many big companies are investigating in quantum computing. Examples including IBM, Amazon, Google, and also many national labs and funding agencies are also very interested in this direction. For example, DARPA has recently announced a BAA for quantum benchmarking, and NSF also has a special call for quantum interconnect. At high level, many countries have announced their quantum strategies, including United States, France, and China. So I started my quantum computing research at UCSD, and I have to say I'm fortunate to work at UCSD. So UCSD has been leading the quantum computing research for many years. We have John Martini's group. The group partners with Google and is one of the best group in the superconducting quantum computing. And they demonstrated the quantum supremacy in 2019. And we also have the Microsoft Station Q on our campus. The site was first established in 2008 and focuses on the theoretical research about topological quantum computing. So recently, NSF Quantum Foundry was located in UCSD, and in 2019, this center has a group of faculties from multiple departments working on the next generation of quantum technology. So despite the great progress made in quantum computing in recent years, quantum programming is still hard and error-prone. So here on the left figure is a screenshot of a bug report of the teleportation program from IBM's Git repository. And bugs has also been reported in other open source quantum projects. On the right-hand side is a figure gives the details of this kind of teleportation programs. And you can see here, this program is quite simple. It only has 3 qubits, like Q0, Q1, Q2, and it has only 6 gates, the Hadma gates, this kind of CNOT gates, and also this kind of classical control gates about X and Z. So, and besides, it has only 2 measurement gates, measurement states operations. And the bug report says that the last gate of X and Z were interchanged unintentionally by the programmer, leading to incorrect results. And as this is already one of the simplest quantum program, it's like the hello world program in the classical world, and we can see mistakes can still be made in such a scenario. So thus, tools for testing and debugging are essential for quantum programming, so that programmers can make correct programs in an easy way. So in early talks today, I believe you have learned about verification in quantum computing, from the verified quantum compiler to the verification of the quantum ramp. And here we remark that testing is not verification, and they are different. And especially software verification may guarantee the correctness of a program. because it will consider all possible executions under all possible inputs, and it's usually very expensive. But testing, on the other hand, is usually cheaper. For example, after you write a program, you can run it a few times and with some test inputs, and to see like whether the program can give you the outputs you expected. And usually testing is a little bit weaker, but still like quite useful considering its lower computation cost. And okay, and here like we next review some basics and the mathematical notations we will be using in the discussion of the testing methods. And especially like in quantum computing, a program variable is a qubit, and a qubit has two base states, and these two base states span a two-dimensional Hilbert space. And then we could have a quantum program state, and this quantum program state is a state of multiple quantum variables, like multiple quantum qubits, and it's a state like based on the tensor product of the individual states of each qubit. And as a program state can be probabilistic due to the branches and loops in the quantum program, usually we will use a density matrix to denote the weighted sum of possible states. And besides this variable and states, we also have two common operations. And the first one is called quantum gates, okay? And it's usually defined by a unitary transformation. And like we can have, usually we can have single qubit gates, like the Hartman gates, we have just the same, and the two qubit gates are like the CNOT gates. And besides the quantum gates, another special component of the quantum programming is called the measurement. Okay, and the measurements are the key to extract information from a quantum system. And especially you can think about a quantum state of a qubit system. And it could be huge of the exponential, which increases to the exponential of the number of qubits. But we cannot directly extract all these informations directly. And we can usually like probe the system using this kind of measurements. And then these measurements can only probe limited information. Like if we have n qubits, we can only have n informations from the system at each time. And this kind of, also these measurements could also, could probably destroy the tested states. And so like with this kind of preliminaries, we now want to talk about how can we test a quantum program states, okay? And on high level, you can think about this kind of quantum, like program testing is to match a program state like rho prime against the expectation from the program rho. And one natural thought is to leverage the quantum state tomography, the QSD, in quantum information processing. And QSD has been the cornerstone of quantum state characterization for years. And it can help give a full characterization of the program state we are interested in, but usually it's very expensive. And it requires to repeatedly like conduct a state preparation and also the measurements many times, okay? And another problem here is if you think about like when we do the program testing, we hope that we can test multiple parts of the program simultaneously, like in one run. But when we use this kind of quantum tomography, for each check, we need to repel the states, and that will create a lot of efficiency problem, okay? And especially like we need to do this kind of checks sequentially, okay? And to fully leverage what programs may have in mind, we could also like learn from the classical testing and debugging techniques. And especially like in classical programming, writers write assertions to convey their expectation about this kind of program states, saying like this rho is what programs have in mind, and we could turn this role into an assertion and insert it into our program. And this kind of assertion is a predicate on some program variables at a place in a program. And if the predicate is satisfied, then it will pass. Hopefully it will not affect the state of the program. And if it is not, then we know there's a bug here and we should abort. So it seems that there are a lot of similarity between the classical assertion and the possible quantum assertions for testing the debugging. But here I want to highlight that there are key challenges could be different. And especially in classical assertion, the key is to have a full coverage of all possible program inputs to increase the testing thoroughness. While in quantum computing, we could just assume that one input is tested. And the reason is usually this kind of input information is already encoded in the operation as a part of the program. Okay, so at that level, we could think that if we want to build this kind of framework, we could use a similar high-level framework as a classical testing, but we need to develop a whole set of low-level technologies. And especially if we think about the classical assertion, we directly borrow this kind of classical assertion to describe a quantum state in a quantum program, then we can see there are a lot of limitations. And we just introduce two previous studies on this kind of assertions, quantum assertions. They try to use this kind of classical assertion to describe the state we could have. And due to this kind of limited expressively power of this kind of classical description, usually we can only describe the state of some special pure states or some special 2-qubit states. Okay, and on the other hand, this kind of assertions, when we have multiple assertions in a program, we need to test it in a sequential way. We cannot test it in one run. Okay, and especially without carefully designed, this kind of assertion checking may destroy the tested states. Okay, to this end, so we hope to have a new approach. And for this new approach, we want to have strong expressiveness power. So the language should naturally describe the complex quantum state properties. And it should be also enable us to do efficient checking, and especially when we have multiple assertions in one program. And our solution, the key here is this kind of projection-based assertion, which strike a balance between the expressiveness and its efficiency, okay, compared to the previous strategies, okay. And to understand why projection is a good solution, I want to use a more complicated motivating example to show you what kind of assertions the programmer may have in mind and why this kind of information cannot be easily described by classical assertion or the tomography, the QST, okay. And here, the example here is about the chemistry simulation. And it is a very important application of quantum computing. And suppose here, we want to simulate 2 electrons on 4 orbitals. And we want to use each qubit to represent the state of this kind of orbitals. And we can easily see that for 2 electron state, this state could be a valid 2 electron state, as we only have 2 ones. It means that the third and the fourth orbitals are occupied. And this one is another valid 2 electron states, which shows that we could have the second and the fourth orbitals being occupied, while this one is not a valid 2-qubit states or 2 electron states. Rather, it's a 3 electron states because we have 3 ones here. Okay, and based on this reasoning, we can easily describe one of the possible assertions the program can describe. And especially this kind of assertions could tell us about what kind of valid solutions they could have by this kind of program. And especially this kind of valid solution should be in this kind of subspace, which spans all this kind of six valid states, okay? And this subspace is much smaller than the original space, which with this kind of 4 qubits, we can have 16-dimensional qubit space, while this kind of subspace only has 6 dimensions. So based on that part, we could do testing and debugging. Okay, so it seems that the key is the subspace. So if we know the subspace, we could do a lot of testing and debugging in the right way. And here, with this kind of connections, we select the projection-based assertions. And here, I just want to tell you a little bit about the definition and the property of this kind of projection. And especially this kind of projection operator is a very common linear operator. And you can find its definition in almost every linear algebra textbook. And it tells you that in a Hilbert space, this kind of projection can map a state onto a closed subspace of the original Hilbert space. And usually we use this kind of P to represent this kind of projection and also the subspace. Okay, so you can see based on this definition, projection, you have 2 dual properties that fit well with this kind of assertions for testing and debugging. So the first one is it has this kind of one-to-one correspondence between the closed subspace of the closed subspace and the projection in it. Okay, so it naturally describes this kind of subspace. And the second property is called this kind of, is based on these projective measurements. And the projective measurements tell us that if the state we want to test is in that subspace, then after this kind of projective measurement, it was still in that subspace. So we will not change that state. And that gives us the power to test multiple assertions in one run, okay? And also, I think I already covered this part, why we use this kind of projection-based assertion. It gives us it matches perfectly with our expectation. It gives us strong expressively power, and it also enables this kind of high runtime checking efficiency. So based on that insights, so we have provide a simple language extension that makes it easier for programmers to express their expectation using projection. And our language primitive for projection-based assertion is quite straightforward. It's basically a projection P over a set of qubits, like Q bar. Okay, and especially when we have a program, this S1 to SL are a set of statements in our program, and we could insert multiple assertions into our program. And the assertion could be only on a subset of the qubits instead of all qubits, okay? And we also give the semantics of this kind of projection-based assertion. And especially tell us that when we have this kind of assertion, we will create a projective measurement for it. And if the measurement outcome is true, then we should continue. And if the outcome is false, then we should abort and report the termination locations. And in this way, we could know how to do debugging and testing. Okay. And here, I just want to give you more about the projections from the theoretical side. And one of the key questions we want to answer here is actually how many executions do we need with a set of assertions? And as we know, the quantum program are probabilistic, and usually we need to have multiple measurements to define the states. And here the good news is usually the number of executions we have to conduct is pretty small. And especially from the basic quantum mechanics, we know that the probability of observing the true outcome is a trace of this kind of projection and the density matrix rho. And if we run it k times and without observing any false outcome, then the probability is pretty low. Okay, and in our paper, we also quantitatively evaluate this kind of statistical properties of checking such a program with multiple assertions. Okay. And here, like we also discuss about this kind of approximate projection-based assertion. And this kind of approximate can come from different kind of perspectives. The first one is like in nowadays for the next quantum next machine, like the machines are with errors, right? So when we execute one operation, one gates, the gates could have errors. And also like a lot of programs, the quantum algorithm itself comes with this kind of approximation. Okay, and usually we only know that a state could proximately in one of the subspace, but not exactly. So in that case, our projection could still work, and we also give the statistical analysis about the number of executions we need to carry out. And here I also want to give you some insights about like why this kind of approximate projection is useful. And it's based on the trace non-increasing of the quantum operations, saying that we know that at one state of, for example, in like we tested the program, we know that this kind of trace difference is pretty small. Then we know that the final results, after we execute more statements in the program, the final state should be also like pretty small. Okay, so this kind of trace non-increasing property is also like one of the key to this kind of approximate projection-based assertion. And the trace also tells us like whether like the measurement will there's a correlation between the trace difference and the measurement, what information the measurement could tell us. Okay. And before is more about the theoretical part of the projection-based assertion. And now we also want to discuss some of the practical implementation issues. And remember, we want to do this kind of assertion at runtime during the program execution on real quantum devices. And the key problem, the key conveyed here is there are some practical issues when implementing this kind of projective measurement. And especially there are two major constraints. The first one is called limited measurement basis, and the second one is called dimension or like rank mismatch. Okay, and the first one, like the limited measurement basis, is about like most quantum, like physical quantum computers can only spot like direct measurements along a fixed set of computation basis. And for example, if our measurement is about this kind of 0, 1 basis, then we can directly measure this kind of qubits to implement this kind of measurement. But however, like if our measurement is in the X basis, like we cannot directly implement it on the physical quantum computers. And the way to solve, and the second constraint is about this kind of dimension mismatch. And this the dimension mismatch tells us that, for example, if we have n qubits, then we will have 2 to the n dimensional space. And here is tells you like how we get the 2 to the n, right? For each of the qubit, it could be in a superposition of the 0 and 1 states. And that's how like we have 2 to the n. But when we measure 1 qubit, then for that particular qubit, it could only be in like 0 or 1 states. And that will like reduce our like space from 2 to the n to the 2 to the n minus 1. Okay, and because we can only measure an integer number of qubits, then like when we have a physical quantum devices, we can only like have direct spot for this kind of projections of like of rank equals to 2 to the 0 to 2 to the n minus 1. Okay, we can only have this kind of letters. And but like as we know, like a projection can have all the way from 0 to 2 to the n. So there are a lot of ranks cannot be directly spotted by this kind of physical measurements. And here just to give you one example, and this P have a rank of 3, and 3 is not in the it does not equal to 2 to the power of integer. So this one cannot be directly implemented on a quantum device. Okay, To this end, so we introduce several transformation techniques. And the first one is like we want to first solve this kind of measurement basis problem. And the high-level idea is we could use a unitary transformation to adjust the measurement basis. And we have a proposition here. And it says that if we have a P of rank 2 to the N, so suppose like the rank mismatch problem, we will solve it later. So if it is the rank equals to 2 to the number of an integer, then there exists a unitary transformation so that we could turn this kind of projection into to diagnose it and do the measurement directly in the computation basis. Okay, and here is just one example. And suppose that what we want to do is to check whether state is in the 2-qubit Bell state, and we cannot directly like do this kind of projection on quantum devices. But what we can do is we could apply like a CNOT gate and a HighLevel gate first, and then then the projection is turned into the 0, state. And this 0, state can be directly checked by measuring the 2 qubits and to see whether they are in the 0 states. Okay, and this would be the circuit we want to insert into our program to do the checking. You can see like it's made. We will apply a CNOT and HighLevel gate before the measurement, and we apply this kind of gate again after the measurement. So as long as the state is in the projection, then this circuit will not not change the original state. Okay. And we then want to solve this kind of dimension mismatch problem. And the high-level idea is we could combine 2 projections to implement a projection with a small dimension. And this kind of, we also have a proposition here, saying that like if we have a projection P, which has a rank smaller than 2 to the N minus 1. So then there definitely exists some projections that is on the rank of the 2 to the N. And based on their intersection, we could create our assertion. And basically, like when we have our assertion like on P, and it could be transformed to a sequence of checks from P1 to PL. Okay. And but there are still one corner cases, which is like if the rank is higher than half, like half of the Hilbert space. How can we do it? How can we match it? And the Paris solution cannot work for it, because like we only have the least rank we can have is 2 to the N minus 1. So if it's larger than it, then we cannot do it. So the solution here is actually quite straightforward. The key here is to use another like a CNOT qubit and then apply the assertion combination. So if you think about it, when we insert one CNOT qubit, it will increase our original space from the 2 to the N to 2 to the N plus 1. And in that case, we now map the case will be the same as the original cases. And here just one of the previous example we have here. So it's if you still remember, this kind of projection P has a rank of 3, right? And the original space has a dimension of 4. And now with an additional CNOT qubits, and now we are in the Hilbert space of dimension of 8. And by combining this P1 and P2, we can directly we can prove that it will be the same as the original P. And here you can see P1. P1 is quite straightforward. Its checking is just based on to test whether the CNOT qubit is in 0 state. And we can directly see, we can propel a CNOT qubit in 0 state, and this does not need to be checked. And here is this circuit for this P2. And I will not go into the details about this kind of projection. Okay. And in our paper, we also have some other transformation and optimization techniques. But here I want to sum up and to say like what is the take-home message for this kind of projection-based optimization. And I want to tell you that actually this kind of assertion and like this kind of assertion-based testing and debugging is very useful, and it's based it has very good expressiveness and efficiency power. But generally speaking, this kind of testing is fundamentally difficult, especially if you think about it. When we do the measurement, we can only probe limited information from the original state. Okay, and the good news is when we design this kind of checking and testing, we are not going to get all information about the state. And this is a significant difference between the classical and quantum assertion, right? And we only want to know whether the assertion is in a subspace, and the programmer will tell us what is the subspace. Okay, and this kind of projection assertion is like a more quantum assertion design for the quantum programming language. Okay, so another interesting news I want to share with you is when we design this kind of assertion, we want to use it for testing debugging. But later, there are some other works showing that this kind of assertion methods could also be used for error mitigation and program optimization. And especially recently, this kind of assertion techniques has been applied to our molecule simulation quantum program, which is a collaboration from the HighLevel and the Cambridge Quantum Computing in their optimization. And you can find that when we apply this kind of assertion, it could decrease the errors significantly. Okay, so maybe later we can find a lot of other usage of this assertion. Okay, so it's quite interesting and a very promising fields. Okay, so thank you. That's all for my talk. So any questions here?